This is Porterville College, Physics 102A, Chapter 6 homework problems. Starting with number 29, it's a center of mass problem. Here's the formula for center of mass. It's the sum of every mass times its position divided by the sum of the masses. So we plug in the numbers for each mass. The first one, the second one, and the third one. Divide by the sum of the masses and get 1.3 meters. Number 33. What minimum force is needed to accelerate a bicycle? What is the system's momentum at that time? So this is the average force. It's Newton's second law says it's change in momentum over change in time. Change in momentum is change of m times v, but since m isn't changing, we can move m to the outside of the change term. So it's m times change in velocity over the time interval. So 105 kilograms times 15 meters per second over 8 seconds, and we get 197 newtons. Momentum at that time is going to be mass times its velocity, so 105 kilograms times 15 meters per second, and we get 1575 kilograms meters per second. Number 37, a baseball goes in one direction, leaves the bat in the opposite direction. Find the impulse imparted to the ball. One thing you have to be careful about is that it's changed direction. So let's call its initial direction negative, or its initial velocity negative 34.5 meters per second. In that case, final velocity will be positive 39.2. Impulse is change in momentum, mv1 minus mv0. Factor out the m, so it's m times the difference in velocities, final minus initial. And again, remember, if one of those is positive and the other is negative, it's going to be adding their absolute values. So we get an answer of 10.69 kilograms meters per second. Number 43. There's the net force applied to a hockey puck with a mass for a certain amount of time. Part A gives it initially at rest, find its momentum. Part B gives it an initial velocity and then find its momentum. Okay, so this first part up to where my pen is on the page is just general. It goes for both parts A and B. So we've got the force vector, the mass, the time interval. The impulse is delta p, change in momentum, which is force times time interval. Impulse then is p minus p naught. So we get p equals p naught plus the impulse. So a general expression that can be used for both parts A and B is right here where my pen is pointing. P equals p naught plus, and there I've solved for the impulse. When you take the force vector multiplied by the time interval, you get 1.53 in the x direction, 1.08 in the y direction. Now let's apply this formula to both parts A and B. For part A, p naught is 0. So that just becomes 1.53 I hat plus 1.08 j hat, kilograms meters per second. Applying this formula to part B, we need to figure out what p naught is. So p naught is the initial velocity times the mass. And so here I have initial velocity in its vector notation times the mass. And then we're adding the second part, which is what we solved for already up here, the impulse. So you should get 2.02 I hat plus 1.31 j hat, kilograms meters per second. Number 55 is next. '55 is a conservation of momentum problem. 130-gram meteoroid it's going to break into two pieces. So if one piece is 55 grams, I have it here moving to the right, then the other piece is going to be 130 minus 55, so 75 grams. We know the velocity of the 55 gram piece, so let's find the velocity of the 75 gram piece. Conservation momentum starts like this. The sum of the momenta before the explosion equals the sum of the momenta after the explosion. So it was initially at rest, so the left-hand side of the equation, the initial momentum is 0. That means that after the explosion, the total momentum is also going to be 0. We have on the right-hand side m1 v1 plus m2 v2. We solve this for v1, and we get negative m2 v2 divided by m1. That negative sign just means that it's going to be in the opposite direction that the second meteoroid went. So when we solve this, we get negative 0.477 meters per second, or we can just say 0.477 meters per second in the negative x direction. '59 is a collision problem. This is a totally inelastic collision where there are two cars and they end up sticking together. So conservation of momentum. Again, we start with the sum of the momenta before the collision equals the sum of the momenta after the collision. m1 v1 plus m2 v2, but the second car doesn't have any velocity, so v2 goes to 0, that term goes out, equals, on the right-hand side of the equation, we just consider it to be one big tangled car that has mass m1 plus m2, and it's going at some speed, v prime, and we want to solve for v prime. So you take this equation, solve it for v prime, and you get m1 v1 divided by the sum of the masses. And we get 1.61 meters per second. Number 89. It's a pretty straightforward center of mass problem. I've already given the formula in another problem prior to this, so I haven't rewritten the formula. But center of mass is always the sum of every mass times its position. So here we have two of these masses divided by the sum of the masses. And so you should get, when you plug those numbers in, 0.400 meters. Number 93 is a center of mass problem. For this one, you know where the center of mass is. It's at the pivot. And we need to find out where is one of the masses. So if you look at this diagram that I've drawn, I've put the pivot, it seems most mathematically convenient to make the pivot the center of mass at 0. So x1, the mass that we know its position, we'll put that at negative 2.8 meters because it's to the left. So x2 is going to be some positive number, and we need to find what x2 is. We start with the center of mass equation. Sum of them, each mass times its position divided by the sum of the masses. Now, it'll be mathematically convenient that we set the center of mass at 0. So we plug in 0 right there. So 0 equals this fraction. If 0 equals a fraction, it doesn't matter what the denominator is. In fact, algebraically, the next step would be to multiply both sides of the equation by that denominator, m1 plus m2. And it goes away. So now we're left with 0 equals the numerator, m1x1 plus m2x2. And we solve for x2. x2 is the negative of the ratio of the masses times x1. And when we substitute in those values, we get positive 2.063 meters. So the second person on the seesaw is 2.063 meters from the pivot on the other side. Number 97. This is center of mass, two-dimensional. So we need to apply the center of mass equation both in the x direction and the y direction. Here I've drawn a diagram. The origin is right here at the lower left-hand side. And here's person 1, where I've got the circled 1. Here's person 2. You get a sense that the center of mass is going to be somewhere in between them, closer to the more massive person. So let's find the x center of mass. Then we'll go on to find the y center of mass. X center of mass is m1x1 plus m2x2 divided by the sum of the masses. We substitute in those values, and we get 54.16 meters. Now, for the center of mass, the y component, m1y1 plus m2y2 over the sum of the masses. And we substitute in those values, and we get 28.01 meters. Now that we know the x-coordinate and the y-coordinate of the center of mass, we can give a final answer. And I've given it both as an ordered pair and in vector notation. 54.16 meters and 28.01 meters. Or if you put that in vector notation, we can say the r vector of the center of mass is 54.16 I hat meters plus 28.01 j hat meters.